Hey there! Welcome to the 7th video of our quantum physics series. We're thrilled to be exploring the fascinating topic of quantum gravity and the quest for a unified theory of physics. As always, if you enjoy this video, please give it a like and don't forget to subscribe to our channel for more exciting content in the future. So let's dive right into the world of quantum gravity. The quest for a unified theory of physics has been going on for almost 200 years. The first person to propose such a theory was the late Lord Rutherford, who suggested in 1907 that light could be described as particles or waves, depending on its wavelength. This idea was later adopted by Einstein, who demonstrated that electrons are tiny objects with mass which radiate energy and emit light. Today we know these two phenomena as photons and electrons, respectively. What is gravity? You might be wondering what gravity is. The best way to describe it is by comparing it to other forces. Gravity is like the force that causes objects to fall when they are dropped from a height. This is similar to how people fall when they jump off a high building or cliff, but in this case, gravity pulls everyone down rather than just one person at a time, as happens with jumping. Gravity can also be thought of as holding planets and moons together in orbit around stars or planets. Like how two magnets together will attract each other's north poles, even though both have different magnetic fields. What is quantum? Quantum physics is the study of the fundamental nature of matter and energy. It's a branch of physics that deals with the study of atomic and subatomic particles, often referred to as particles. It's also known as quantum mechanics, an area in which scientists study how atoms, molecules, and other microscopic objects behave at the quantum level. Atoms are actually made up of smaller parts called electrons. What is spacetime? Spacetime is a mathematical model that combines space and time into a single continuum. It is used to describe our universe, and it's an important part of quantum physics. To understand spacetime, you first need to understand what the word space means in this context. Space consists of 3 dimensions: height, z, width, x, and depth, y. These 3 coordinates can be written as vectors xl, yom, zek, where 0 corresponds to x to 0 on the left side of your coordinate plane. My 0 corresponds to xc, 1. 2 corresponds with your money. 2 corresponds with 0 corresponds with 0. How to tame quantum gravity? The problem with quantum gravity is that it's hard to tame. Quantum field theory describes black holes, the early universe, and even big bangs. But what can we do with this information? There are 2 main ways we can use quantum gravity. We could use it to describe the Big Bang itself by having its singularity be a black hole, as per current cosmology. Then we'd need to know how far away from us that singularity was when it formed. So if you're reading this article, then you've already been there. We could also look at what happens when matter comes together in pairs or triplets, like photons, then apply those rules of attraction between particles, photons, into our understanding of space-time itself, as well as its geometry, which includes time. Is there really a unified theory of physics? There is no unified theory of physics. Quantum gravity is a very difficult field of study, and the theories that attempt to unify quantum mechanics and general relativity are called theories of everything or TOEs. They're not really TOEs because they don't fully explain what makes up reality as we know it. Why? Because there are fundamental questions about how we define our universe that cannot be answered by any existing theory. And without those answers, no theory will ever be complete. Can we overcome the Planck scale limit? The Planck scale limit is the theoretical limit on how small objects can be. It's thought to be a fundamental limit on the physical universe, and it's one of the biggest unsolved problems in physics today. Quantum gravity is an attempt at unifying quantum mechanics with general relativity, the other pillar of modern science. This would allow us to explain why space and time seem to exist even though they're really just empty space, like water. We need to think about quantum effects in cosmology and quantum gravity. Quantum effects are also important in cosmology. The geometry of the universe is quantum mechanical, and this has consequences for how it evolves over time. In particular, quantum gravity can explain some of the features we observe today. For instance, black holes and other exotic objects that seem to defy our understanding of gravity. Quantum gravity is key to understanding black holes and other exotic objects that seem to defy our understanding of gravity. It's not just about how we understand them on an atomic or subatomic level. It's about what happens at larger scales, such as galaxy clusters or even galaxies themselves. So far, we have discussed about the nature of quantum gravity in cosmology and quantum effects in condensed matter. These are just two special cases of a much bigger problem: how to tame quantum gravity. In order to do this, you need to understand the concept of spacetime. Of course, there is no such thing as one unified theory, because physics is very complicated and there are many different approaches that can be taken by different people or groups of people. But if we want our research to lead anywhere, then it's important that we all try solving these problems together using the best tools available right now. In conclusion, quantum gravity is an exciting and rapidly evolving field that has captured the imagination of scientists and the public alike. While the search for a unified theory of physics is still ongoing, recent breakthroughs in quantum gravity research have brought us closer than ever to unlocking the secrets of the universe. We hope you enjoyed this video and gained a better understanding of the quest for quantum gravity. Be sure to subscribe for more videos on the frontiers of science and technology.